Good afternoon, everyone. Welcome back. Thank you for joining us on this beautiful Friday. We're glad that you're here. I'm Steve,
And I'm Scott.
and together we're Backyard Musings, the Science and Technology channel.
Yeah, and this is, I guess, a science topic, right?
Geology,
Geological science topic. So,
Earth
um,
science.
yeah, it's involving some movement of the Earth in certain areas. So here we go. We're going to talk about this. And Steve says we've talked about this before. So,
Yeah, deep beneath Africa, a massive flow of hot mantle rock appears to be quietly reshaping the continent in ways scientists did not fully expect. What we talked about before was actual physical at the top on the ground. The ground is starting to separate in Africa. This is talking about how and why. New research is shedding light on why parts of East Africa are deforming in unexpected ways, revealing a powerful force rising from deep within the planet. Scientists using advanced computer simulations have confirmed that the African Superplume, a massive flow of hot mantle rock rising from deep beneath Southwest Africa, is shaping how the East African rift system is breaking apart. Would you like to know more?
continental rifting is the process that slowly tears a landmass apart, eventually forming new ocean basins over millions of years. It begins with the stretching of the lithosphere, Earth's rigid outer shell. As this layer thins, the upper crust fractures, producing earthquakes and visible cracks, while deeper regions can flow more slowly and smoothly.
Yeah, that's what we talked about, those cracks and those earthquakes before.
Right.
Geophysicist D. Sarah Stamps explains that this contrast in behavior depends on time scale and stress. Earth's lithosphere behaves in different ways. For decades, scientists have expected most deformation in rift zones to occur perpendicular to the direction of the rift, essentially pulling the crust apart sideways. The East African rift system, the largest active continental rift on Earth, does show this pattern. But long term GPS measurements have revealed something puzzling. Parts of the region are also shifting parallel to the rift itself.
Hmm. To investigate, researchers turned to detailed 3D thermomechanical models developed by Tahiri Rajo now a postdoctoral researcher at New Mexico Tech. His simulations show that this unusual rift parallel motion is driven by northward mantle flow tied to the African superplume.
Hmm.
Hmm.
This finding helps resolve a long standing debate about what forces dominate the rifting process. Some scientists have argued that relatively shallow forces known as lithospheric buoyancy are responsible. These forces are linked to the elevated African superswell and variations in rock density. Others have pointed to deeper mantle traction forces caused by the horizontal movement of hot rock beneath the surface.
Earlier modeling work in 2021 suggested that both forces are important. Buoyancy explains the expected sideways stretching, but it could not count for the newly observed parallel motion. The latest study fills that gap by identifying mantle flow from the superplume as the missing driver.
The research also explains a related phenomenon called seismic anisotropy. Anisotrop. How do you pronounce it?
Anistrop, anis, an,
Anisotropy?
anisotropy,
Anis-
anisotropy,
Whatever
anisotropy.
Scott said. Where, seis- where seismic waves travel faster in certain directions because of how rocks are aligned underground. In East Africa, that alignment matches the direction of the superplume's northward flow, offering further evidence of its influence.
Quote, we are saying that the mantle flow is not driving the east-west rift perpendicular direction of some of the deformations, but that it may be causing the anomalous northward deformation parallel to the rift. This is according to, oh geez, here we go again, Rajo and Narasan. Uh, Going on with the quote, we confirmed previous ideas that lithospheric buoyancy forces are driving the rift, but we're bringing new insight that anomalous deformation can happen in East Africa.
The findings were published in Geophysical Research Letters on October 14, 2005, highlighting how processes occurring hundreds to thousands of kilometers below Earth's surface can directly influence how covenants break apart above. A separate study, also published in 2025 in Geophysical Research Letters, focused on how smaller blocks of crust, known as microplates, behave within the rift. Using dense global navigation satellite system data, scientists found that the Victoria microplate, located between major rift branches, is slowly rotating counterclockwise at about 0.0583 plus or minus 0.0293 degrees per million years. So that's like a quarter inch per year.
Whoa!
Hey.
Slow down.
Hey.
But that's still movement, though. That's pretty crazy.
Yeah.
All right. The study shows that most of the deformation is concentrated along the edges of this microplate, where faults slip at rates of about 1.8 to 2.2 millimeters per year. That's about 0.07 to 0.09 inches per year.
Tiny.
While the interior remains, I'm sorry?
I said tiny.
Yeah. While the interior remains mostly stable with only minor stretching in some areas. But when the stretching's happening, I wonder if it gives off some kind of a, seismic activity.
Like earthquake or heat?
Okay. It's like what we had the other day, right? A week or so ago. We had some rumblings going on.
Yeah, we don't even know what that was, folks.
Yeah.
We had rumblings a couple days in a row.
Yeah, earthquakes or sonic booms or
maybe it
we
was
don't
a
know.
rift.
Yeah, maybe it was. So anyway.
This rotation helps explain why deformation in the region is not perfectly aligned with the rift itself. Instead, movement is slightly angled, reflecting a combination of forces acting at different depths. It also suggests that the breakup of Africa is not a simple uniform process, but a complex interaction of deep mantle flow, surface forces, and the shifting motion of smaller crustal blocks.
Quote again, we're excited about this result from Dr. Rajawanarsen's numerical modeling because it provides new information about the complex processes that shape the Earth's surfaces through continental rifting, and that's according to a guy named Stamps. So okay. Yeah,
interesting.
Pretty crazy.
Earth science stuff.
I wonder if it's just happening there. I don't know. Of course, I imagine every time we have an earthquake, we get some kind of rifting, right? But anyway, it's fascinating. It's just weird stuff.
I was telling Scott the other day that I never took a biology course in my high school or college. I took earth sciences, which I thought was fascinating, and I still think is fascinating.
I took biology twice. We won't go into why.
Did it involve breaking a ruler across your bottom?
No. It was in middle school or junior high, we called it. And by that time, I had gotten past all of that. My bun had been beat enough, so I tried to turn a different direction. But no, I just didn't. The teacher and I just did not hit it off. And again, I took the same course from a different teacher and got a almost 180-degree different grade. So just one of those deals. And I wasn't going to do it, but my dad said, you need to take this course over. If you're telling me it was the teacher, take the course over, see how it goes. That way we'll know that you're just giving me a bluff or it's the teacher. And so, yeah, for whatever reason, this teacher and I usually got along pretty well with all my teachers, even if I didn't do well in the class. But this teacher and I just did not get along very well. So, but anyway, it is what it is. So, good story.
All right, folks. Thanks. We'll see you tomorrow.
See everybody later. Take care. Have a good night. Thanks.